Did you look something up?
No, we're trying to figure out where Tim is.
Oh, he's a play.
The play thing. Yeah.
Like 10 o'clock? Yeah.
I think they have like 2 showings or something. I don't get that. Unless is there an open bar? That one's on recording, by the way.
There was no bar. You'd probably be having class there.
No, probably not today. Yeah, today it's a lot of clear liquids and Advil. that's what we're doing today. I had to make serious decisions in the middle of the night whether it was worth it to get up to go to the bathroom.
Serious decisions is in.
My body hurt so bad, and like once I was in bed and kind of just stuck there, I'm like, okay, this is all right.
Do we have to wipe the bedpan, or we just get off?
So you want to know? This information you're actually interested in?
Let's just keep it hypothetical.
Okay, so we were talking about difference between Unix system calls and Windows system calls last time. So of course we have forking. Got to work that into every lecture. Examples: MS-DOS. We were talking about some of the differences between server-side, server class operating systems and single-user operating systems, and some of the decisions those operating systems have to make. So there's not like a correct way to write an operating system. If you're an MS-DOS or Windows-based operating system, the NT kernel, or even the Mac OS, which is based on Unix, but it's really probably a modified version of Unix because, generally speaking, the Mac operating system is for single users, right? We're sitting in front of our computer, we're using this thing. We wanted to make decisions that are going to benefit us, just us. Whereas the Unix operating system in general, being a server class operating system, its default, if you will, its original construction was to benefit many connected users at once and have them all tricked into thinking they're all getting full CPU time. So it becomes some very interesting, some of the decision making you have to make when you're writing an operating system to determine who are we pleasing and what do we have to do to make them happy. So MS-DOS, single tasking, which that's not acceptable by us anymore. So this is actually a really easy model. When the computer first boots, we get the shell loaded. Shell would be similar to what we were looking at with the terminal. We have simple method to run programs. The idea of creating multiple processes didn't exist in the early MS-DOSes. So, so unfortunately, Abe, no forking. No forking in MS-DOS. Huh?
Boring.
It's just so boring.
You could just install Perl and then you can work.
It's MS-DOS is like the church version of operating systems. I get one giggle out of that. Everybody's like, I'm not sure if I'm supposed to laugh. That's a Christian worldview, by the way. Right? No forking in church. I have to be really careful to enunciate these words. you know what the mic to this makes it onto confessions. Here's an audio clip from our class today. It's a little bit fuzzy what he actually said, but it would actually be a funny video to go through my classes and do the unnecessary censoring.
I don't think we need the unnecessary.
I never actually say the words. There's a lot of innuendo. But, because you've seen those things on YouTube and stuff with I think the funny one is the from Sesame Street, the Count. You seen that one? Yeah, that one's a good one. Where they just censor stuff and then your mind is filling in the blanks. I posted something on Facebook on Wednesday. I came into this classroom to grab my laptop. It was uploading the last lecture. And there was 2 guys sitting in here, older guys, probably 45 or something like that. And they were talking. I walked in the middle of the conversation. And the quote that I walked in on, if you didn't see it on Facebook, was, I've thought about shooting homeless people again. I walk in on that line. They were photographers. And so they were talking about,
At least that's what they want.
no, they had all their photography. They went to great lengths to look like photographers if they weren't. But yeah, that was a funny quote to walk in on. So again, with MS-DOS, and this is something we're going to talk about when we talk about the specifics of how memory management works, used a single memory space because we only had to load one program into memory at a time. We didn't have to do fancy crap with memory. Like you have, let's say 2 megabytes of memory back then. So you have 2 megabytes of memory. As long as your program would fit inside of 2 megabytes of memory, we're good. Because nothing else is getting loaded. Small portion of memory had the operating system preloaded into it, so that was unusable by system program or by user programs. But then all the rest of memory was one big open bucket to put whatever program you wanted to launch into it, but only one. So when we look back to MS-DOS, by today's programming standards, it's a very simple operating system, which even makes it more entertaining from the historical sense we talked about. Kind of Microsoft and the how they made their money initially. When Bill Gates walked into a meeting with IBM and said, we want to license you Windows, well, not Windows, this is DOS. We want to license you our operating system. They didn't even have a name for it at the time. We want to license you our operating system on a per machine basis. And IBM said, no problem, the real money's in the hardware. Microsoft didn't have an operating system at that point. That's when they went out and bought this. They paid for DOS. They got it cheap. By today's standards, $50,000. But if we look at DOS, and we're going to look at how some of these things are implemented, as a class, we could probably write DOS. So, we could split 50 grand. This is 15, 16 ways, no biggie. Nobody's going to pay us that for it now. Wrong time, wrong place. So, in any case, MS-DOS by today's standards is a very simple operating system. Like this is what I was saying. Loads programs into memory, overwriting all but the kernel. So the early memory management literally just set aside an amount of memory specifically for the kernel, for the operating system, and everything else loaded into the rest.
Was DOS mostly written in assembly, or what was it?
Well, DOS would have been written in C. It was post. Yeah, it was post C. Yeah. Now let's call it 96%, 96.4% certain it was written in C. The bootstrap would have been in assembly, but that's still true today. The part that actually loads, goes from, the BIOS to the actual operating system being loaded. So you have that little bootstrap program. That's got to be written in a low-level language. All right, MS-DOS execution, wasted space, we just said that. So here's an example of a Unix-based thing. This is the one that had the little daemon guy, the FreeBSD daemon I showed last time, the competition between the Linux Penguin and the better FreeBSD guy. So this guy being a Unix variant, which right out of the gate is going to be more geared for server class type situations. By default, it's multitasking. And really, we have to think about this multitasking slightly differently than we would think about our modern day multitasking. The reason being, it was multitasking because we had multiple users using the operating system at once. Not necessarily providing the functionality of having one user running multiple tasks, which we can do today. So for instance, let's say you have, if you're out at a terminal, if this is your entire operating system experience, no graphical stuff, that your whole screen is taken up by this. You could only do one thing at a time, correct? But let's say you had a program that was going to take forever to run or something like that, or take a half hour to run. You could launch it and run it in the background today. In the earlier days of Unix, you couldn't do that. You would just start your program and walk away, come back and check on it. So you could only run one program at once per user. Okay, because I can log into the machine, Amish can log into the machine, Abe can log into the machine. We can all be logged into this machine, and we would have our own shells that we can run our program in. So it was multitasking from that perspective. Only later did it become multitasking within multitasking, something like that. Because what we can do then is, if we had a bunch of stuff running in the background, we can go and look up what processes we currently have running and then bring one of them back into the foreground. So it was really the equivalent of in Windows, when you go down and you click on the things from the very bottom, all the programs you currently have running. It was doing that from the command line, is what later multitasking was in Unix. But in the earlier days, this concept of multitasking really involved having one program per individual user using the system. So user login invoked user's choice of a shell. We talked about shells a couple classes ago. You would have a startup script, and that startup script would pick your preference. In the early days, it was always sh was the shell. Oh, Abe.
Saw that.
Saw that. I was waiting for it. The shell executes the fork system call to create a process. Okay, then executes, and these are system calls. That's why it's so. Maybe get your head out of the gutter for a second so we can finish this one. Executes the exec to load the program into a process, and then shell waits for process to terminate or continues with user commands. So that was what I was just talking about, and once you started something, it would be running continually. So if we were out here at the terminal and I go ahead and load a program, this program just launched for me. This is a text editor. And I can type crap into it. And then when I go to, well, I'll just quit it. So I'm finished with this program. So I'm closing the old school version of Microsoft Word. Now I'm back to the command line. That's when that process was killed. And now I'm left with my original thread, if you will. It wasn't a thread back then. It was an actual physical process. But now I can type stuff in again. Also an interesting thing, and this is more of a historical element from Unix, and I want to show this in, let me just do it in here. If we remember like our C-based Hello World program, usually it was I think this will work, except you don't want to name it text. So there's our Hello World program we just wrote. Now, interestingly, let me do something real quick. I think it is, yeah, I'll just call it. Oh, is that not right? Yeah, whatever, doesn't matter in this example what I'm trying to give you. Oh. So if we look at this code, notice the difference between our Java version of Hello World and our C version of Hello World. So we have our main method. Remember, all programs begin and end with main. This stuff in here is the equivalent of string array args. This first guy is the argument count. The second guy is the actual array of arguments, because old school C arrays, so char pointer pointers, this is a double pointer. They didn't know how to keep track of how many elements were in them. So we had to pass along how many elements were in it. But the most important thing here, the thing that we should be noticing, is the difference. Ours in Java is public static void main, returns nothing. Old days, main always returned an int. This is an error code. It lets us know, I mean, this is the simple Hello World program, but in more complex programs, it lets us know whether everything went well. Does that make sense? So this guy would have returned an integer, maybe a 0 if things were fine, a 1 if things weren't, or maybe 1, 2, 3, 4, 5, up to 50 if there was 50 different things that could have gone wrong, that type of stuff. And then you look up those error codes. We kind of see those error codes today in web pages. If you've ever gotten like a 401 error or something like that, there's a whole list of HTTP known errors, standard errors. So this would kind of be a similar example to that. And the reason for this is it was common to call Unix programs from within a shell script or something like that. And you might want to wrap it inside of an if statement and make sure everything was fine before you moved on. Okay? So that's why these guys returned an integer. So processes would have an exit code of 0 for no error or greater than 0 if there was an error. And then you can respond to that. So that was common in Unix programs, whether it was a system program or just a normal program that a user wrote. And that's why the return type was int. In fact, not really until, in fact, let me try something real quick. I don't think it's legal for me to not return an int with GCC and C. Yeah.
Well, that's because you still have return.
Oh, yeah. I still think it's not. I still think it's not going to be legal.
We'll probably compile.
Yeah, has to be an int. I think if we did this as,
compiled, didn't it?
huh?
It just threw out a warning.
Yeah, it may have compiled.
But yeah, it won't.
It did compile. It still wasn't happy with that. So in any case, it was very common, if not basically required, to have a return type be an int. Because every program we would have written would have been a program that could have been called by another program, which isn't really common for us today. When we write applications today, most of our programs are standalone, right? This idea of having a program call another program, calling another program, doesn't really exist. We have our programs call methods inside them. Well, that existed back then too. We had procedures and functions, and we could call those as well. But at the end of the day, it was commonplace to return a value. So FreeBSD running multiple programs, useless. Well, maybe not totally useless. So if we think about it, we have 3 people connected to the operating system at the same time. Each of those 3 people would launch a program. So we want to think about this from a memory management perspective. So forget about what the slide actually says. It's kind of a stupid slide. But with DOS, we had this concept of we had a chunk of memory built for holding the operating system, and then the rest of the memory is free to load the single user program. So that's relatively, in the world of memory management, easy, right? No searching, just is program size less than or equal to the size of your memory? If yes, load. If no, error. Not enough memory, because this is before virtual memory. Good reason, because the hard drives weren't big enough to really support virtual memory. But, so this was back in the days, actually this was previously to the days where you had a computer that had a 120 megabyte hard drive and 1 megabyte of memory. Could you even imagine? 120 megabyte hard drive. We couldn't even get the opening credits of the movie we just stole. I wonder if we had the crazy people back then that set up real crazy arrays where they had, it's like, yeah, I got 40 100 megabyte hard drives linked together. But back then, nothing was anywhere near that big. You buy I think Microsoft Windows came, which was, let's call that a later operating system. Windows 3.1, I want to say the install disk was either 1 floppy or 2. 2 floppy disks. So the total installer for an operating system was under 3 megabytes. Pretty legit. How big is our operating systems today? I think you download Windows 8, and Windows 8 is something like a 2.4, 2.5 gigabyte download, then it unpacks.
Windows 3.1 was 6 floppies.
6 floppies. Look at Windows 3.0. That had to be less. Might be dating myself here. But whatever. Windows 8 probably installed as 5, 6 gigabytes ish, something like that. So in any case, when we have to deal with a more complex memory management system where even in our example we have 3 simultaneous users and each of those users is going to launch a program, those programs have to get loaded into memory somehow. Well, what do? Well, we have some options. We can, the simple way we might say, well, let's just partition memory into 3 pieces. So rather than having one big chunk of memory, we're going to have 3 smaller chunks of memory. And the size of the maximum size that a program can be is 1/3 size of memory. But that is us supporting 3 users. What if we have 50 users? We have to divide memory up into 50 pieces. So we probably would want to look at something more dynamic, where okay, you have 100 megabytes of memory. Actually, you'd have 1 megabyte of memory back then. But so you have 1 megabyte of memory. User A. Here we call it process B. So user B loads process B. Process B has a memory requirement of X. We're going to go ahead and partition memory to hold that program, leaving ourselves this chunk of free memory. And we just keep coming in, keep coming in. That has its own downside though. As a user finishes their program, we have memory already partitioned. Unpartitioning memory is actually expensive. So usually we would just leave it partitioned and hope for the best, that future programs fit in about the right footprint. So you could actually run into a situation where you have enough free memory to launch a program, but not any single partition big enough to hold it. So we'll talk about that stuff in a lot more detail when we discuss memory management, the specifics of it. But at the very least, we can see that to support something like this is far more complex than supporting the simple MS-DOS memory management scheme, right? Got to load one program, no biggie. Now we got to load, even in the simple case, 1 program per user logged into the system. Well, how many users are we going to have? Well, who knows? Well, it becomes interesting. System programs provide a convenient environment for program development and execution that can be divided into file manipulation stuff, status information, file modification, programming language support, program loading and execution, communication, and application programs. Most users' view of the operating system is defined by system programs, not the actual system calls. So what this whole slide talks about is what we said kind of almost, I think, day 1 or day 2 of class, talking about the difference between the operating system and a distribution. We think of Windows 8 as being the operating system when the actual operating system is the NT kernel. But from our perspective, the NT kernel is meaningless to us without all of the applications around it that support it. So it's the distribution that's important to us. System programs provide a convenient environment for program development and execution. That's stupid stuff. Stupid stuff. User goals and system goals. User goals operating system should be convenient to use, easy to learn, reliable, safe, and fast. So that's from our specific perspective. System goals operating system should be easy to design, implement, maintain, as well as flexible, reliable, error-free, and efficient. I'm not necessarily sure I agree with the easy to design. Maybe if we had our druthers, we'd be okay with that, but not at the cost of the user. So, but even these 2 statements are, pretty malleable from the perspective of user goals. How many users do we have on a specific system? And that's where we have to start changing our perspective on what our goals are for the end user if you're the operating system writer. Similarly, as these goals change, as the user goals change, the system goals have to change as well. That's where I think the easy to design side of things kind of gets thrown out of the window. Operating systems, I think, by default are not in our realm of easy programs to write. Now that isn't to say, this kind of goes back to my little saying I say often, the whole all hard programs are made up of a bunch of easy parts. So if you looked at the source code for Windows or the latest version of Linux or Mac OS, you would recognize pretty much all the parts of the program. You'd see if statements, you'd see for loops, you'd see integers. Just happens to be there's a zillion of those lined up together that are under the hood solving some sort of interesting problem. Okay? But these two goals are in conflict with each other, and they need to kind of balance themselves. Modern operating systems have almost real-time balancing. Depending on the current user load on the system load can change. We see this kind of at the high level if we are running a virus scan on our computer, and we start launching user applications at the same time. Typically, the virus scan goes into the background and has a very low priority for running on the CPU, so that our system programs are getting more CPU time, so we feel relatively happy. Whereas if you've ever defragmented a hard drive, can you reasonably use your computer at the same time as your computer's being defragmented? Well, why doesn't that get a lower priority? What happens when you're defragmenting a hard drive? What's the job it's trying to do? Kind of condense everything towards the front of the drive so our access times are faster, right? Well, if most of our user applications are saving and retrieving stuff from the hard drive, and at the same time we're moving crap around on our hard drive, first of all, we now have a moving target. Secondly, we run into that problem we discussed when we have two big files we're copying, and those guys are competing with each other because the hard drive is having to spin back and forth between the two of them. And keep in mind that defragmenting is pretty taxing on your hard drive because you're literally moving millions of files. So it's doing all those little spins that we're talking about. If just comparing, trying to copy two files at once, it's doing that to move between all sorts of files. It's moving them to the front and trying to also group like files together. So there's there's more to defragmenting than just shifting everything to the front of the disk. That might be the easy day one version of fragmenting if you were the first person to write a hard disk defragmenter. So let's just move everything to the front because we know we're at least getting a performance gain from that. But now we try to be a little slicker with it where we look at can we take files that belong to the same program and put them next to each other so that the seek time within, we launch Microsoft Word, we don't have to jump as far to load the next file from Microsoft Word, that type of stuff. All right, so these user goals. Oh man, I jumped. What is happening? There we go. All right, that's what we just talked about. Simple structure, MS-DOS, written by providing the most functionality in the least space. It's not divided into modules. MS-DOS has some structure, its interfaces and levels of functionality are not well separated. So keep in mind that the original MS-DOS was a hobby program written by just some dude. So this guy wasn't really written in a bunch of individual pieces that we can go and modify this, and now we have a better structure here and modify this. We had this kind of monolithic program that ran as a operating system, a shell-based operating system. So again, just like we talked about the memory management side of MS-DOS, the actual full operating system design of MS-DOS kind of had everything piled into one pot. Okay? So updating it, maintaining it became difficult, especially as we moved through the evolution of operating systems. We started relying on multitasking. When we started having to add features to this operating system, kind of shows us maybe the reason why Microsoft started diving into this new technology kernel. I don't know if their day one decision was, hey, let's move everything over to NT eventually. But they kind of kept MS-DOS alive because there were so many programs built for it, and they were already popular, so it was good for business. but they were really modifying an operating system that, by the day's standards, wasn't easy to update. It was error prone. That's why we had the blue screen of death all over the place, or not why, but certainly one of the reasons why we had the blue screen of death all over the place. You had an operating system that was just hodgepodge together. So MS-DOS layer structure, here's your ROM BIOS. So that's actually built into the motherboard. Then you have your device drivers. Now, keep in mind that these device drivers are going to be very simplistic compared to our model of device drivers today. But what's important is, as MS-DOS became very popular, I mean, it was very popular in the early days of desktop computers. I mean, they weren't running any graphic user interfaces. They were running DOS. But you had business offices that had different kinds of printers, and they had scanners. They had all sorts of different programs for reading stuff into their computer. Well, they had to be device drivers for those things. And because there was all these device drivers written for DOS, not NT, written for DOS, it kind of put handcuffs on Microsoft to continue to update DOS rather than being able to dive into a new technology, because they didn't want to have to do what we saw Apple do later on. I mean, when we saw Apple make the jump from OS 9 to OS X, they basically told all of their users, you got to start over with everything. Well, that wouldn't have been good for the bank account for Microsoft. And for years and years and years and years, what was Microsoft? It was the biggest bank account. That was their thing. So they had to maybe quelch innovation at the goal of maintaining compatibility. And maybe that's almost isn't that kind of Microsoft's MO even today? We don't view the company as being an innovation company. It's not in their DNA. And it's not that Microsoft has stupid people working for them. It's because Microsoft was a company built around a single operating system that had ridiculous early success. And because of that ridiculous early success, they were locked into having to stick with, the inferior, let's say, but well-adopted operating system. So it becomes kind of an interesting problem they had to solve. So above the device drivers, we had the system programs, and then on top of that, we had the application programs. Well, application program. I'm not sure system program is accurate here because we had a bunch of system programs, but up here we'd only have one application program running at a time. Layered approach. The operating system is divided into a number of layers. So this would be more of a modern look at operating systems, each built on top of lower layers. The bottom layer is the hardware. The highest layer is the user interface. And everything in between has like the spill-through effect. Okay? And the closer you get to hardware, the less we want users looking at it. Okay? With modularity, layers are selected such that each user uses functions and services of only lower level layers. So they would talk to the layer below them. Solve problems in terms of the layer below them. So an application program would solve problems in terms of system programs, which would solve problems in terms of device drivers, which would solve problems in terms of the actual hardware interfaces built into the motherboard, which would solve problems in terms of the CPU. So Unix system structure. So we have the users at the top. This is still not dealing with graphic user interfaces yet. The users would interface with shells and command compilers and interpreters, system libraries, so things at the command line, which would then interface with system call interface to the kernel. So notice that these three layers, the sandwich right here, is what they're calling the actual kernel. So this would be a synonym for the actual operating system. These guys would be application, these are people. This would be application programs. So the kernel, the top layer of the kernel is system call interfaces to the kernel. In that we have signals, signal handling, I/O systems, terminal drivers, file systems, stuff, CPU scheduling stuff. So kind of the meat of the operating system. Below that we have the kernel interface to the hardware. So these are the application programs of the operating system. So these are the things that make the operating system work, and these things can be written in a high-level language. These guys would be written in a high-level language, these system calls, because all user programs would be written in terms of system calls, which would talk to these different aspects of the operating system. Ultimately, those aspects of the operating system would talk to hardware, which is controllers and device controllers, terminal controllers, device controllers, memory controllers. A terminal controller would be for like external monitors, things like that. I think I pointed out something like Dr. Locklear has in the other room. He has a whole, if you walk into this advanced lab over here and you turn right immediately, those really old computers along the wall are old terminal servers or dummy terminals. So we have one box that's the actual server. It doesn't work, and he won't get rid of it. So there's one box and you have a bunch of monitors and keyboards linked to it that we're all using that single terminal server. So Unix, limited by hardware functionality. The original limited by hardware functionality, the original Unix operating system had limited structuring. The Unix OS consists of two separable parts, the system programs and the kernels. Kernel consists of everything below the system call interface and above the physical hardware. Provides the file system, CPU scheduling, memory management, and other operating system functions, a large number of functions for one level. So this stuff right here, this one little mini paragraph or sentence, whatever, really tells us what the pieces of an operating system are, the functional pieces of an operating system. So even in looking at this, the original version of Unix was certainly a more complex system than DOS, but was not necessarily what we think of as being modern operating systems. Modern Unix operating systems, modern Linux operating systems are not where this guy was back then. They're substantially more modular today. And the reason for that is we can release system updates, right? It's common for us when we get updates to Microsoft Windows or any of our other operating systems, they can upgrade individual aspects of the operating system because those things are modular. So they release a system update, it overwrites a portion of the code associated with the operating system, and now that particular code still solves the same problem it solved before, but might solve it in a better way. That make sense? But see, the important part of that, if we think about that, let's say, we put this in terms of building a car. I don't know a lot about cars, but I think this example should work. There are parts in a car where you can buy various performance level versions of that part, correct? Whether it's mufflers or whatever. There's the same part in a car, but you can buy 10 versions of this, probably at higher and higher and higher prices that give you better performance or something. But each of those parts has to have the same interfaces so it can hook into the current system in the correct way. And then what happens after that could be different, right? So all mufflers, for example, have to hook into the system one way, and at some point they have a pipe that shoots the stuff out, that releases the carbon monoxide and all the other crap. So the actual interface has to remain the same, even if the muffler design is different. Same thing goes with operating systems. When they release an update to the file system or something like that, well, it still has to plug into the existing communication channels that that are the recipients of file system calls. So you can't change the inputs. You can change the way it handles those inputs, but within a single version of an operating system, you are still limited to making those modules fit together in a consistent way. There's a standard. So that actually can limit the way that an operating system, through updates, can be handled. That's why even today you have major updates to operating systems. That was the opportunity. If we just look recently at for the phone, iOS 7 to iOS 8. While we had iOS 7, there were several software updates where they could update portions of iOS 7. iOS 8 was an opportunity to restructure aspects of the operating system so that now we can have new updates released for that maybe deal with more inputs or something like that. So it really becomes an interesting thing where you can't just think about compatibility today. You have to think about what your ability to upgrade in the future is. And we see this fairly often. How many of you who've done quite a bit of programming have ever used a function call, you might not see it as much in Java, but you might. But certainly in older languages like C and C++, you might see a function call that takes 5 inputs, of which you actually pass it 3. Because 2 of them are fairly meaningless to you. You might just pass it null, null for those last 2 because you know they're not applicable to the problem you're solving. But that particular function accepts 5. So it was built to be a little bit future ready, if you will, future proof. Layered operating system, we already talked about this. This is just a picture of it. Microkernel. So this would be more of a modern approach to operating systems. Moves as much of the kernel into user space. So now we're kind of separating. We almost think about the operating system, which we've been calling the kernel. We split that kernel into 2 pieces. One piece is what's really, really the operating system. And the other piece is kind of what's almost the user side of things, but still the operating system. Okay, so we split it. Communication takes place between user modules using message passing. Benefits: easier to extend a microkernel because actually the actual kernel, the actual operating system is very small. You know, whatever the core functionality of an operating system is squeezed into this microkernel, and everything that surrounds it, the layer right above that is, let's just call it very complex user applications. Probably not written by users, probably written by the application designers. So easier to extend the microkernel, easier to port the operating systems to new architectures. That's only maybe a half-truth. It'd be easier to port the microkernel to other architectures because you just have to rewrite that portion of it, but you're still going to be reliant on the end user programs or the kernel-esque user programs to be ported over to the other architecture as well. You might be able to make the argument that the things that work directly with hardware are going to have to be modified for moving to a different architecture, moving from PowerPC to Intel, for example, hardware architecture. So those things that talk directly to hardware absolutely, certainly need to be changed when you move from Intel to PowerPC or vice versa. Where the application programs that sit one layer above that maybe only need some slight tweaks to be recompiled successfully for that new architecture, because you're not talking directly to the hardware architecture. Kind of make sense? Let me just finish this slide real quick. More reliable, so less code running in the kernel mode, so less things that can really break this whole system. More secure, because you're having to control less stuff. Detriments: performance overhead of user space to kernel space communication. Essentially, we've added one more layer of communication at the cost of everything else being a little bit more structurally sound. Make sense? All right, we'll talk about the midterm on Monday. I think we're going to have it in class on Friday. I'm going to try to put up a study guide of things I want you to know today. Actually, maybe right after class today. I also owe those of you who are in 325 the same thing. So I'll get those up today. So we'll talk about the midterm on Monday. So kind of know what to expect and what it's going to look like. And same thing with 325. We'll talk about that on Tuesday. All right, I'll see everybody next week. Have a good weekend. Make sure you watch me on Bear Grylls. What? Which part? I just golfed. It could have been on Bear Grylls.